Also, I probably should have led with this, but I think that, I don't know, I've thought about this a little bit. I think that this is not a video for somebody who doesn't know calculus that is trying to learn calculus, okay? You don't have to know calculus to know what's going on. You don't have to know calculus to follow along with the video. But if you're looking to learn calculus, I think that this is not the video for you. Let me know if I should make that video, but that's not going to be what we're going to do today.
This ain't what you want. Project. This ain't what you want. This ain't what you want.
Hello, people. Everybody, welcome back. So today we are going to, you may have seen some stuff about Karl Marx so far from me recording last night. We are going to be continuing with that today. Now, everybody else, we're back. Alright, so I feel like last night I read, what does Fahe et al. Mean? Who's Fahe? That's my question. What does this mean? And others. Okay, so who is Fahe? Some guy? I don't know. I don't care. Sounds like, I don't know, one of Marx, a Marxist. Fahe is probably a Marxist. Yeah, a follower of Marx, because he was one of Marx's friends or followers or whatever. We caught him. He's a Marxist, everybody. Get him. Okay, so Mr. Fahe says that Marx never used the term, differential calculus? In his mathematical papers, his history of calculus can be understood in terms of thesis, antithesis, and synthesis. Okay, that's a good for him. That's not how I think of math, but, you know, that's the beauty of math. You can think about it however you want to, you know what I mean? So, that's, you know, good for Marx. Three historical phases in the development, mystical differential calculus of Newton Leibniz. Okay, that makes sense. And purely algebraic of Lagrange. That's kind of base. That is purely algebraic. And then he didn't know about Cauchy. Legacy. I can't imagine there's much legacy going on here. But let's see. To put dy dx equals 0 firmly and point blank does not enter their skulls. I would say that is true because you could make it equal 0 over 0, but that's kind of boring, so that's why we don't do that. You look for a more interesting answer, you find one. You see what I'm saying? And he's calling my way of thinking one-sided. Fuck Frederick Engels. I'll beat the crap out of this guy. What's his deal? I want to fight him. Oh, he's a friend of Marx. Oh, he's a leading authority on Marxism. Well, I'm a leading authority on math, okay, over this guy. We can fight if he wants. Historian of science, that's a fun job. She states that, contrary to many claims by Engels and other publishers, Marx's work did not solve the historical and conceptual riddle of calculus. Well, of course not. Another mathematician observes that Marx seems to have been unaware of the advances being made by continental mathematicians in the foundations of differential calculus, including the works of Cauchy. So yeah, he doesn't really, because Cauchy is important. See, look at him, he's got his own picture there. It's nice. But, you know, like Cauchy sequences, stuff like that, it's important for limits and these kinds of things. So yeah, for him to not know, that's like, yeah. So like, it's good. Shout out Marx for like figuring it out on his own, but that's why you gotta stay with the culture, you know what I mean? Like, you gotta stay up to date so you don't accidentally do something that somebody knows. Actually, though, that's not my recommendation to my amateur mathematicians out there. I would say you should work on whatever you want to work on the most. As an amateur mathematician, that should be your priority, is like answering the questions that are most interesting to you. But yeah, if Marx he couldn't keep up with being a professional mathematician, you know what I mean? And neither can I, but gotta know about Cauchy, my dude. Anyway, then Marx's definition of the differential anticipated some of the developments in mathematics. So that doesn't really say a ton. Like it says he was smart, you know what I mean? But he wasn't smart enough to contribute. He was just smart enough to see. He had an understanding of what calculus was early. You know what I mean? Like earlier than most people did. He was like right up there with the mathematicians for a minute, probably. Not like we're not dealing with a brilliant mathematical mind here, I don't think. And I've read a bit of the manuscript, and we're gonna look at it. But who is Fahe? Calculus, a Marxist approach. Ooh, that looks good. Hey, I'm a Marxist. Maybe we'll read this. I'm kind of hungry. 1 second. Also, I probably should have led with this, but I think that, I don't know, I've thought about this a little bit. I think that this is not a video for somebody who doesn't know calculus that is trying to learn calculus, okay? You don't have to know calculus to know what's going on. You don't have to know calculus to follow along with the video. But if you're looking to learn calculus, I think that this is not the video for you. Let me know if I should make that video, but that's not going to be what we're going to do today. So this is calculus, a Marxist approach. Let's see what a Marxist approach would look like to calculus. You know what I'm saying? Frederick Engels wrote, yeah, we read this already. Firmly point blank does not enter their skulls to put E equal to 0 over 0. No, it does. We do put it 0 over 0, and then we make it something else. No Dylanette, I don't know what that means. Nor was he a mathematician. He was, though, an economist, historian, and philosopher. Tools of philosophy, he tackled calculus. I would have used the tools of... Can you hear somebody walking around upstairs? It's really annoying. I would have used the tools of economics to tackle calculus versus philosophy, but to each their own, you know. To better understand the writings, we must understand Marx's philosophy. Here, this is what I want. This is the kind of thing this is what I'm interested in for this video. Because, like, I'll talk about the math, but the math's it's kind of lowbrow stuff, to be honest with you. So I'm not super concerned with the math. His sort of materialism, which under Hegelian, see, remember, also just a disclaimer, everybody, that I don't know how to read. Okay, so it's tough, but we're gonna hang in there together. In Marx's view, all sensation of perception is an interaction between subject and object. The bare object, apart from the activity of percipient, is just a mere raw material, which is transformed in the process of becoming known. Knowledge, in the old sense of passive contemplation, is an unreal abstraction. The process that really takes place is one of handling things. We may interpret Marx as meaning that the pursuit of knowledge is not, as has been taught, one in which the object is constant while the adaptation is on the mere part of the knower. On the contrary, both subject and object, both the knower and thing known, are in a continual process of mutual adaptation. He calls this process dialectical because it is never fully completed. Okay, I feel like we didn't need to read all that. That was brutal. So yeah, we get it. There's an object and subject. There's things and actors and things acted upon. Okay. That's not that difficult to comprehend. Marx seemed to be unaware of the enormous development of calculus during his own century. The latest original source he examines is the 1813 version of Lagrange's theory of analytical functions. Beyond Lagrange, Marx relied fairly on standard textbook by this other guy. Marx's ignorance for the crucial period. Marx's mentor, translator of the Communist Manifesto, Samuel Moore, shout out, Communist Manifesto, was also unaware of the contemporary developments. Okay, so for what he had, he was doing good, right? That's what it seems, but he just didn't have everything that he needed. I feel like he wasn't as focused on math as you need to be a mathematician. I don't know. The last historical manuscript is essentially an appendix to the first, with the focus on a perceived ambiguity of the terms limit and limit value. Through these writings, Marx relied on detailed examination of a couple of special cases, extracting generalities from specifics to guide his understanding. Okay, that's not how you develop a rigorous math proof, but that is how you show that you are understanding things, you know what I mean? Which I think was kind of his goal. To better, I don't know. This is a statue dedicated to the labor commune. It's a stone. That's cool. Well, it's less reading, right? So the fact that every one of his sources has a strong geometric flavor. All right. Evidently, Marx preferred algebraic arguments to geometric ones. He demonstrated a firm grasp of algebra with his calculations of the derivative a to the x, which is based on a loose argument that employs series expansions. Okay, not bad. While it is clear that Marx could calculate the derivative of a function by algebraic manipulations, he was disturbed by the meaning of it all. For example, he calculated the derivative of ax as follows: x1 is greater than x. Okay, so yeah, this is x plus 1 minus x, y plus 1, or corresponding y differences. You get the rise over run, slope equals a. Okay, so now this is the deal. You say like x1 is a little bit greater than x, right? And then you make that amount greater, smaller and smaller and smaller and smaller, and so it's basically 0. Okay, and then oh no, now it's 0 over 0 equals a, and oh, that's not true. It's right. It's meaningless. Every trace of it is meaningless and disappeared. So yeah, replace it with dy dx. Right. Replace it with the slope. Replace it with the symbol for a slope. dy dx. Right there. Logical. Marx thought deeply about the fundamentals of differential calculus and was well aware of what he was doing when he wrote 0 over 0. Okay, that doesn't mean that you should do it though. Okay, so continuing on the differential. Most interesting for anybody teaching calculus because Marx explored the meaning of dy dx. Basically, calculating definition of a derivative from first principles. We've kind of talked about this, but without the notion of a limit. Okay, so consider f of x minus f of a over x minus a. If when x equals a, the bottom becomes 0 and the top should become basically 0 too. And so you get 0 over 0, right? And he's like, oh, this is a big problem, which it is. And this is what limits are for, but he did not see this as a fraction. He saw it as one symbol. Probably smart. dy dx is a way to write it. You could write it as y prime. There are several ways to write it. Seeing it as a symbol is the right intuition for this, is to see it as a... Okay, so with that being said, his only reservation about 0 over 0 was that it does not refer to the function being differentiated, nor its argument differentiated y, nor its argument x. Hence, he was prepared to allow the use of dy dx to try to emphasize the point. He often wrote 0 over 0 or dy dx as if he were writing dy dx reluctantly. Okay, that makes sense. So he understood dy dx, but he didn't. Alright, whatever. Yeah. Alright. Another feature of his understanding of dy dx is best illustrated by an example. Y equals x to the m power. Dy dx equals m times x to the m minus 1 power. Yep. That's like the common power rule for differentiation. That's like this is a very standard rule in calculus of the derivative definition. So yeah, he could put that together. Dy dx is the symbolic coefficient. Yeah, it is. M times x to the m minus 1 is the real differential coefficient. I mean, it's a fine way to think about it. There's nothing wrong with this way of thinking about it. Symbolic differential coefficient, symbol used to represent the derivative. It's real function, coefficient is a specific function. Okay, we get it. It's one is a symbol and the other is like a value, like a function. That's what's special, is getting the function. Marx made heavy weather of the distinction, which is discussed time and time again in whatever page. But because I read this and I can see how he was doting on this 0 over 0 thing. He's really obsessed with explaining the problem, over-explaining the problem, arguably. But continuing, modern analogy can help us appreciate the point Marx is making. Left-hand side of the equation, dy dx equals mx to the m minus 1 is different than the nature of the object in the right hand. The left-hand side represents an operation to be performed, and the right-hand side represents results of performing this operation on a particular function. That's not like who wrote this like modern analogy to help us appreciate, because that wasn't super helpful. What year did this come out? 2009? Yeah, that wasn't super helpful. I don't know. If that was helpful to you, I don't know, but that seemed pretty obvious. It's a symbol. The derivative is a symbol for something that you did, an operation that you did, okay? And then the integral is to undo the derivative, okay? So that's your calculus crash course for the day, folks. Okay, having arrived at this conclusion, he discussed at length the meaning of d of uz over dx. Okay, basically this is called the product rule in calculus, where it's like you have two functions being multiplied together. How do you break them up in a way that you can take the derivative, which is the derivative is basically to find the slope of a function. So how can you break up a complicated function in a way where you can still get an answer for what the slope is? Okay, that's the question that he's asking here. And it's something called the product rule is the way out of it, which is basically to rewrite the derivative as this, and then it's fine. For Marx, the very nature of this equation needs an explanation. I agree, it's a little bit of a vague formula. We cannot say the right-hand side is the result of differentiation of the left-hand side because we are not told how either u or z depend on x. Yeah, but you don't need to know. That's what the fun thing. He described this equation as a symbolic operation, right. In modern terminology, he is saying that is an operator equation, right? No, it is. This is what he's getting at is this is a formula for like as in like a set of instructions for something for how to. This is a formula for you to use in order to take the derivative of a product of two functions. Okay. So I mean, I guess he's right in saying the meaning of these two operators isn't like equal. This is the next step. You could write it as an arrow. Although Marx tried to teach himself the basics of calculus on his own, the depth and sophistication of his thinking is impressive-ish. It seems like he's getting really caught up on he's getting real stuck in the weeds, you know what I mean? Which is like a common problem that mathematicians have. I've done it before, but I can tell that he's a guy getting caught in the weeds. If you know anything about Marx, he's in the weeds. That's what they say about him. So we know that Marx had the access to some work by Bakerlot. I keep seeing this guy's name. Preparing this paper, we had access to only the French edition listed in the bibliography. Bakerlot. I don't know if I'm saying his name right, but that's how I'm going to say it. Bakerlot. Borkelot. There we go. That's my final answer. Borkelot made it very clear in the opening pages of his work that one uses limits to calculate the derivative of a function from first principles. It appears Marx deliberately rejected these arguments. That's a way of that's a fun way of mathematically problem solving. It's like challenge yourself to find another way to get to the same answer, because there are probably an infinite number of ways to get to any given answer. That might be true. As far as if you knew more math, you could get to any answer you want in any way. Probably. I don't know if that makes sense, really. There's a dog outside. That's a cute dog. I'm looking at the dog. But I don't know if that makes sense from a mathematical standpoint. But it's just like, I don't know, just another reminder to kind of play with things and see what happens, One of those. Because you might be able to find your own answer, like he did. And did he change the course of history with his math? No, but he changed. But this guy was the thinker, changing the course of history for sure. Mr. Marx, Karl. I feel like we're on a first name basis now that I've gotten to know his math. I feel like I can call him Karl now. Can be read as following a thesis, antithesis, and synthesis model. Okay, so we kind of got some of that from this. So let's see. His own treatment of the differential can then be seen as a natural progression from these 18th century authors, even though his history manuscripts post-date his writings on the differential. Glivnenko, I don't know who that is, recognized Marx's approach and noted that Marx solved the question by examining the tradition from algebra to differential calculus and mathematical dialecticality. In mathematics, dialectically. Algebra to differential calculus in mathematics dialectic. Yeah, but that's I don't know who this Glivnenko is. Maybe Marx was the first time he heard about it, but this isn't anything groundbreaking. If Marx was a good mathematician, you guys would have heard about that. You know what I mean? I didn't know that Marx did math. Somebody suggested that I do this video, and I thought this was right up my alley. So thank you for the comments, and now we're doing the video. But I didn't know that Marx was into math, and I know math culture and stuff like that. And we're gonna make a video. I'm gonna make a top 3 mathematicians video. It's gonna be really fun. But Marx isn't in the top 3. Marx isn't on the list. I gotta be honest with you. But we'll keep reading. But whoever Glivnenko is. He's tripping. Algebra to differential calculus and the transition. It's a very natural progression. I would argue it's the next thing to do. I would say so. It's nothing that groundbreaking. Anyway, the first of the history manuscripts begins by comparing the differential of a product treated as. So this is the differential of a product. This is what I was talking about. This formula here. That's the differential of a product. He compared the differential of a product as treated by Newton and Leibniz. So if you don't know, Newton and Leibniz are two people who kind of discovered the fundamentals of calculus around the same time, and they had two different approaches. Newton had more of a physical, an approach that came from physics, and Leibniz had more of a mathematical approach. They wrote symbols differently, things like that, and so it was a hot debate for a while. but now people just, I think Leibniz notation won, but like, Newton's still Newton. You've heard of Newton more than Leibniz, so like the real winner is up to you. So that's the deal with Newton and Leibniz. But they did things a little bit differently. Concluded that both Newton and Leibniz valued differential expressions from the beginning as operational formulae. Yeah. No, they're both taking, right, that's the thing. Marx concluded that they both are the same thing. Yeah, that was the problem. Like, that was the debate, because they were the same thing with two different approaches, and it was like, what's the right approach? That was like in the 1800s, that was the debate happening between Newton and Leibniz. Nation separating stuff here, folks. You guys don't know the history of math, but yeah, that was the deal. Detailed examples treated algebraically followed the manner of Newton and Leibniz that then provide Marx with his empirical evidence. Turning into a general treatment, Marx stated, the general direction of the algebraic method which we've applied may be expressed as follows. Given f of x, the first preliminary derivative we call f1 of x. That's a first derivative. You know what I mean? He's like, this is just him like simplifying things for himself in a way that anybody else would if they were doing these kinds of things. But he's not doing anything wrong. He's just not, like I said, it's okay to do math for fun. I'm not hating on his work at all. Doing math for fun is cool. Yeah, we're not breaking no new ground still. His second history manuscript identified three phases: mystical, differential calculus, rational. Okay, we talked about this already. By now, Marx reached what he believed to be the correct view. Lagrange takes as his immediate starting point for the algebraicization. I've never seen that. That's not a real word, I don't believe. Algebraicization. You would say like algebraize, probably. Algebraicization, though. That's a word I've never seen in my mathematical career, and now I'm hearing it from Marx. So that would suggest to me that it's not a real word, but maybe I'm wrong, because nothing else he said has been anything that's been difficult for me to comprehend at all. So it takes his immediate starting point for the algebraicization of the differential calculus, the theorem of Taylor, outlived by Newton and the Newtonians, which in fact is the most general comprehensive theorem. Yeah, it's Newton's a simpler way of doing it, like limits, I guess, but Leibniz is cooler, I would say. Leibniz is cooler. Newtonian, which in fact is the most general comprehensive theorem, at the same time operational formula of differential calculus, namely the series expansion expressed in symbol coefficients. Okay, so once you get into Taylor, like what Taylor is doing, you have no choice but to algebraicization, but to do an algebraicization, I feel like. But maybe that's just because I know what I know, and I'm not coming at it from like this kind of fresh lens that Marx is, but I feel like the only thing logical, like that's the only thing left to do is like make it an algebra problem. Once you get to the time of like doing Taylor series, you got to see if you can like take some transformations, or like there are things you can do. You start taking Laplace transforms, things like that. You got to get those out of there. Learn algebra, everybody. But okay, 1 second. All right, so let's keep reading here. Given that these phases reveal how Marx viewed the historical developments of calculus. Honestly, that's true. It says more about him than it does about calculus, but it's cool that somebody's writing about these things, and it's cool that Marx, I appreciate that Marx took the time out of his busy schedule, I'm sure, to write more about math. And maybe we should do a little deep dive on Marx here. I don't need a Marxist post on here. That's not what we're going to be doing. But no, I do appreciate Marx for looking into the math stuff, because I'm a fan. You know what I mean? So I appreciate a math fan when I see one, and I see that Marx was working hard being a math fan. So shout out Karl Marx. Okay. Two other manuscripts, one unfinished, deals with theorems of Taylor and Maclaurin. Maclaurin and Taylor are very similar theories. One is just a shift to the other, a way of shifting, I guess. That makes Taylor is a little bit more useful, I guess. maybe I don't know what I'm talking about, but in my experience, it seems like the Taylor series allow for a shift in coefficients that make them more widely applicable than a Maclaurin series. But that's just, like I said, maybe I don't understand, maybe I don't know everything, but from my understanding, in my experience, that's what I've seen. So, all right. Anyway, the lacuna, I don't know what that means. Oh, in further discussion of Lagrange's theory of derived functions. All right, he liked Lagrange, there's nothing wrong with that, but yeah, he was a fan. The lacuna in Marx's knowledge means that he missed the antithesis-synthesis, which occurred after Lagrange. That is, the rigorization of the logical foundations of calculus. As a result, Marx embarked on his own dialectical program in reaction to the deficiencies he perceived in the original work of Newton and others. Yeah, Newton noticed how calculus worked, but I think Newton didn't really understand it. And I think that's what Marx is getting at with this mystical differential calculus thing. I think Newton knew how to take a derivative, but he didn't really know what the implications were. He just was somebody who noticed it. Embarked on his own dialectical program in reaction to deficiencies he perceived in the works of Newton and others, and in isolation reached conclusions different from those commonly accepted. How different? Nevertheless, Marx made a valiant attempt in isolation, and we can only guess at how his study may have ended had he been fully aware of the contemporary text. Well, this is why you have to talk to people. He wasn't from this. It doesn't appear that he was talking to his friend Engels. He's not talking to mathematicians. He needs to be talking to mathematicians. That's his problem. How are you going to get good at math not talking to mathematicians? You can only learn so much by reading, in my opinion. You have to have conversations with people and hear things, different perspectives. I don't know. But maybe that's an opinion, but I don't know. I learn well from talking to mathematicians. So, yeah. So I've been doing some reading on what dialectical materialism is, basically. Basically, the math was inspired due to his thoughts on, well, we're going to get to it, but his ideas on, what is this guy? This was the guy in the middle. D'Alembert, that guy. Oh, see, the thesis is Newton and Leibniz. D'Alembert is the antithesis. Let's open that up again, because it looks like what he was doing is kind of thought experiments about that the drag on a body immersed in an incompressible fluid is zero. See, okay, so paradoxes like that, it's, I think, because Karl Marx's thing is to look for contradictions. This is what dialectical materialism is. It's kind of looking for contradictions between the thesis and antithesis. And then the synthesis is kind of the solution, which is I think the dialectical materialism at play when we discuss the math of Marx. Okay. And then, the other thing I realized here is he was writing to Engels, and Engels is his best friend or whatever, because when we're still going to look through this, but it is very reminiscent of me telling my friends in high school about the things that I learned about in math, on my own outside of classes. You know what I mean? I would learn math on my own for fun, and then I would have nobody to talk about it with, and I would just tell my friends, and they're like, "Dude, I don't care." And it seems like that's what Marx was doing with his friend Engels here, where they're both he's just a philosopher buddy, and Marx is no, but listen to the math. It's fun, and that's what I'm here to do now, is tell you why math is fun, and you should listen. You gotta listen to the math. That's what they'll say. They being me in this context or whatever. Let's keep reading. Let's continue with this paper thing. So why was Marx interested in calculus? According to Marx, performance in mathematics at school was weak. However, somebody else states that Marx's gymnasium certificate said that he had good knowledge of mathematics. I don't know what a gymnasium certificate is, but good knowledge of mathematics, okay. In any case, Marx did not pursue math at university. There must have been a strong motivation to turn to it so late in life. Okay. It's just an intro paragraph. The manuscripts do not give the reader any idea of why he was studying calculus. To find Marx's motivations, we must look elsewhere. This guy, whoever, offers or argues that Marx studied calculus purely for intellectual reasons. Marx worked on mathematics in spare hours for relaxation, often in hours of sickness, struck by the unsatisfactory formulations in the books available to him. He tried a characteristic way to strengthen out the difficulties he had for himself. You know what I mean? Like, that's what a mathematician, what like an intellectual guy who's bright at math will do for fun. That makes sense, like, Kennedy agrees that Marx was interested in math for its own sake. I agree. It's fun because it's fun. It doesn't have to be used for anything. It's just it's an interesting problem, and like, I don't know. I like problem solving, you know what I mean? So that's really what it's about. This view is supported by Marx himself to some extent. In a letter to Engels, Marx wrote, my spare time is now devoted to differential and integral calculus. However, in the same letter, Marx suggested that calculus would be almost essential to Engels' military studies. That's interesting. Probably, if you're smart and doing military studies, you should probably know calculus. That's one of the things that you should know. Although Marx notes deal with theoretical aspects of calculus, at least he had an eye on potential applications. Thinking about militaries. Leon Smolinski examines mathematical manuscripts of Marx, tests the widely held view that it was Marx's influence that delayed for decades the development of mathematical economies and economic systems of the Soviet type. Interesting. Marx's influence that delayed for decades the development of mathematical economies. Okay, maybe. Interesting. I've never heard that argument before, but it's a possibility. Yeah, okay. The development of mathematical economics in economic systems of the Soviet type. So basically, the Soviets weren't doing the math in their economics, like for analysis, and not getting the results that they should be getting because of it, I think is what it's saying. Like, supply and demand prices are off, things like that. Like, quantities are wrong, prices are wrong, things like, maybe that's what they're saying. Marx's ideas and influence kind of stalled from them looking at these things mathematically. I don't know. That seems like not Karl Marx's fault, to be honest with you, that you were too lazy to do the math and look at these things. But that's just my opinion. This, in turn, was said to have adversely affected the efficiency with which they operated. Smolinski found no evidence for the two opposing views that, one, Marx would cast Marx as a mathematical illiterate, and two, claim that he made creative contributions to mathematics. Right. This is a dumb argument. Like, his math wasn't that good. If there wasn't access to other math at the time, maybe he was an influential mathematician to the people around him. That's a possibility. We could have a little Ramanujan situation on our hands. No, we don't. I'm just kidding. It's not that. He wasn't that good. But maybe he was influential mathematically to the people around him. But that shouldn't. Just because he's a Marxist, that doesn't mean that it would stall mathematical economics. I feel like that's I feel like I'm not understanding something, or I don't know, because that's a leap. Smolinski argues that Marx's studies in mathematics began in 1958, algebra, studied calculus in 1963, returned to study of calculus in 1870 to keep abreast with the mathematical school of political economy. Okay. Yet despite his original intent, Marx made little application of mathematics to economics, and he quickly became interested in mathematics primarily for its own sake. Yeah, I get that. So he was learning it to keep up with the econ at the time. Smart. And then it's not his job to be like, Marx did the theory. Somebody else, it's not his job to do the math too. And if he wants to focus on math for math's sake, he should be allowed to do that. So Smolinski accusing him of stalling the Soviet Union is like, this is ridiculous. In his own economic writings, Marx turned to arithmetical examples rather than formal mathematical explanations. Smolinski can find no evidence of Marx writing that he was opposed to mathematical economics. Right. He's not saying he's opposed to it. He just likes math. Indeed, he made pioneering proposals for mathematical analysis of the business cycle. See, that's what he should be doing, and considered that science could only become developed when it is made use of mathematics. I should reread that again. Consider that science could only become developed when it is made use of mathematics. I totally agree with that. If you can't put math to it, you don't understand it, really, I would say. Like, you can understand a physics concept, but if you can't do the math behind it, then, like, you don't really understand what's going on. And it's okay. It's okay to just know things, but, like, real physics is just math. I don't know much about biology and chemistry, but I can tell you physics is a lot of math. Okay, so in the early 1920s, Soviet model builders took Marx's lead in turn in mathematics. Most notably, never heard of that guy. Almost without exception, the mathematical economists were critical of Joseph Stalin's forced industrialization and incurred the wrath of Stalin. Of course they did. Of course. Oh, Kondra was put to death, and others received long terms of imprisonment. No good. Others abandoned economics together. See, and he's going to blame, and this Leon Smolinski guy is going to try to blame Marx. Marx's influence that they've delayed for decades. No, it was literally Stalin killing the guys who were doing, or putting to death the people who were doing the mathematical economics, because the math says that he was wrong, because that's how being right and wrong works. The math will say. The math will tell you the answers. All right? That's the good thing. Another explanation for Marx's motivation, he wrote to Engels, in elaborating on the principles of economics, I've been so damnably held up by errors and calculations that I have applied myself to rapid revision of algebra. I have never felt at home with arithmetic, but by making a detour via algebra, I shall quickly get back into the way of things. Okay, so yeah, he's, trying to understand things better so that he can do his job better. It sounds like he's a hard worker, sick, respectable. Perhaps in pursuing economic studies, he revised algebra. From there, it was the natural step to explore the basics of but basically, when you play around with algebra for long enough, when I learned calculus, when I learned what a derivative was, I honestly, felt like such an idiot, because it's like, oh yeah, that was so obviously the next thing to do when you're playing with these equations, you know what I mean? If somebody just said to, mess around with this equation for a while and see what happens, I probably would have come up with the derivative, I feel like. You know what I mean? So it is the next natural step, is to start exploring the basics of calculus. Yeah, word. No evidence that Marx intended to publish his notes. He revised his work so extensively is typical of his approach in learning any subject. Yeah, it's good practice, for sure. During the last decade of his life, Marx filled his microscopic handwriting, almost 3,000 pages, these manuscripts comprising almost exclusively of notes on his reading. In his later years, this reading became obsessional. He no longer had the power to create, but at least he could absorb. I don't know what that means. Okay. I was reading, and I was reading out loud, but I wasn't really understanding it. And, so I don't know. Whatever you took from that, cool. Commentaries. Several prominent authors found Marx's math sophisticated enough to warrant attention. Glivenko argues Marx's approach to the concept of the derivative is similar to the approach taken by whoever about 50 years later. The same point is made by Kennedy. Struick makes a strong case, discounting I don't know what that word means. Marx is an original contributor of the reconciliation of different opinions over the meaning of such a basic notation as differential. It's not, there's not really a debate over the meaning. It's just debate over, the perspective on what you understand what a derivative is, I think. But, okay. Kennedy discussed how Marx interprets differentiation as dialectical process. Okay, we've been over the dialectical process, you know what I mean? You got two different ways of thinking about it, and you're like, hey, here's a new way of, this is the common, the logical conclusion is the synthesis between the thesis and antithesis, you know what I mean? It's basic, it's simple communism, you guys. There are 3 commentaries. These authors argue for a dialectical approach to mathematics and science in general for background information. Okay. An extensive paper, Math and Mathematical Economics, yeah. It is not well known by mathematicians, economists, or historians that Marx was interested in calculus. Yeah, no. Maclean's now standard biography of Marx makes no mention of the manuscripts. The aim of this article is to inform readers about Marx's effort to master differential calculus, demonstrate a clear understanding of the mechanics of calculating derivative from first principles. Yeah, that's pretty basic. We get that by now. Algebraic arguments to geometric. He preferred algebraic to geometric arguments. Clear understanding of the chain rule, Leibniz rule for differentiating the product of several functions, which is the product rule thing that we were talking about, I think. Thought deeply about the meaning of the derivative and was very particular about the meaning of mathematical symbols used in differential calculus. Yeah. Wrestled the issue 0 over 0 as many mathematicians did before him. Yeah. He did not approve of limiting arguments. Perhaps he regarded the limiting arguments set forth in standard texts as insufficiently rigorous. Well, limits are pretty sufficiently rigorous, I would say. You don't need to reinvent the wheel. Just take a limit, I guess it's okay to not like limits. Limits are annoying. Limits suck. But you didn't need to. I feel like when you're learning math, understanding indeterminate forms and 0 over 0, that's one of those things where you should not worry about a ton. Not worry about a ton and just keep working. And you'll kind of get a grasp of what 0 over 0 might mean later. Okay. That's my thoughts on that. Okay, let's see. He would have the same objection in many calculus texts these days too. Marx might prove to be a difficult student in a contemporary calculus lecture, but tutorial discussions would not be boring. Yeah. Marx would be disappointed that more than 120 years later to write dy dx equals 0 over 0 still does not enter our skulls. I feel like it does, we're just it's not useful, so we're ignoring it. But let's see what let's go to the paper. Let's go to the paper and see what he says. And then this was me reading about dialectical materialism. See, I do my research. I haven't read Das Kapital, but I know what Marxism is.
This ain't what you want. Project. This ain't what you want. This ain't what you want.
Is there a difference between? Hear me out here. I don't know if this is a debate in the scientific community or what the deal is with this. Is there a difference between a telescope and a microscope? For real though. I get that one thing is looking at big things and one's looking at small things, right? But they're both making something look bigger so that you can see it, because you can't see it with the naked eye, right? So if you pointed a microscope into space, would it work as a telescope? That's my question. I don't know. Is this a debate, where it's oh no, a microscope is not a telescope? Are they the same, are they inverses of each other? Because I think that they're the same thing. Just something that, there's some dialectical materialism for you. It's a dialectic, there you go. Anyway, back to Marx. So I was reading about, the capitalist mode of production. I know this stuff. I know how Marx works, theory of labor, the working class, the proletariat, communism being the dialectical, logical solution. The synthetic solution would be a communist utopia, you know what I mean? And that's the lesson of Marx, Okay, so now we'll take a quick crack through his math, see what he's got to say. We don't need the preface to the Russian edition. We don't care about that. Long preface. Okay. Engels to Marx. Dear Moore. Was that a nickname for him? No, we read this before. Compliment you on your work. Clear as day. One-sided by these gentlemen thing. To put dy dx equals 0 over 0. Point blank does not enter their skulls. It is clear as zero that dy dx can only be the pure expression of a completed process if the last trace of the quanta x and y has disappeared, leaving the expression of the preceding process of their change without any quantity. Okay, yes, so things should equal 0. Calculus says, well, hey, it doesn't have to equal 0, it can equal something else. And he's like, I agree that it should be 0. Yeah, they're now, so Hegel, I looked that up too, because they were Hegelians or something. Hegel is a philosopher. So old Hegel guessed quite correctly when he said that differentiation had for its basic condition that variables must be raised to different powers, and at least one of them to the second, or 1/2 power. Now we also know why. Well, that's not true, but it's true if you want to do any of the fun rules, 1/2 power, that's a tough power, bro. If we say that y equals f of x and X and Y are variables, and this claim has no further consequences as long as we do not move on, and X and Y are still pro tempore, in fact, constants. Only when they really change, yeah, right. Not the relation of the magnitudes, but of the variability. First derivative shows this relation as happens. Of course, of real change, given change. The complete derivative shows it is generically true, pure, hence we can come from dy dx to each delta y delta x. So that's just change in y over change in x. It's basically the same thing as dy dx. But the delta is like supposed to be a small number, so you're supposed to put in like a number for how much you want it to change. And then the idea is that as the number you want it to change by gets closer to 0, it goes to 0 over 0. This causes some problems, but then you can take like what are called limits that give you the derivative of a function, which would give you the slope, rise over run, as we see here, when the change is infinitesimally small. Okay. That's kind of how calc works. That's what's going on. Because a curve like y equals 2x, or like y equals x, has the same slope the whole time. You know what I mean? It's like 2 or whatever. But a slope of like something like x squared, a parabola, its slope's changing. It's the rate at which it's increasing is more over here than it is down here. You know what I mean? Down at the base, it's moving slowly up. And then once it's over here, it's moving quickly up. See what I'm saying? It's changing. And so when you try to calculate this change at a given point, you just get 0 over 0, and it's nonsense, because 0 over 0 can be anything. It's not necessarily 0, because it could be infinity, technically, because dividing by 0 should give you infinity. It's what you would call an indeterminate form. And so these guys they're kind of meandering about what it means to be an indeterminate form. I don't know who Moore is. He's talking to Marx. Calls Marx Moore. Is it a pet name? And closes an essay by Moore, another Moore. Oh my gosh. It's like putting together pieces of a puzzle here. See, Fred. That's a normal name. Sam. What is his name then? Is it Fred or Sam? Fred. His name is Fred. Frederick Engels. Who is Sam? Sam, as you saw, immediately criticizes the analytical method applied by me just by pushing it aside, and instead busies himself with the geometrical application, about which I said not one word. Yeah, but the geometric applications are still fun. That's what I just described with my hand there, was the geometry of it. Then there's the equations that go with it, and the equations work, but the geometry can tell you things too, because you can expand on geometry and then do calculus again. That's like calculus of variations, calculus on manifolds. It's geometry stuff. Don't hate on geometry. Riemann would not be happy with you, Mr. Marx. Manuscript on differential calculus. Okay. X increases to x subscript 1. Y increases to y subscript 1. Here we consider the simplest case that appears. Y equals ax. When x increases to x subscript 1, you can subtract this. You're essentially subtracting this equation off of this equation. Okay. And that gives you this equation. Now, when y subscript 1 is barely bigger than y, and x subscript 1 is barely bigger than x, right, then we run into the problem of differentiation. Now allow the differential operator to occur. That is, we let x subscript 1 take on the value of x. So set those equal to each other. Now it's 0, right? So you get 0 times a equals 0, but also a. When you do this to x and y, this becomes 0 equals 0, making the differentiation, then removing it, therefore leads to literally nothing. The whole difficulty understanding the differentiation operation of the negation generally lies precisely in how it differs from such a simple procedure, when therefore leads to real results. Okay, I don't really know what he's saying there, but he's saying that he notices the problem that every other mathematician noticed at the time with the 0 over 0 thing. Okay, so we're going to call this 0 over 0. Instead of calling it a, we're going to call it delta y over delta x, this triangle. And then this delta y over delta x equals a, the limit value of the finite differences of the variables. Okay, so now he is cheating and using limits, because I thought he did this without using limit. And now he's like, and then a is the limit value. Okay, but you were supposed to do this without the limits, Karl. What the hell, Karl? Since a is a constant, no change can take place, hence none can occur on the right-hand side, which has been reduced to a, right? Under such circumstances, the differential process takes place on the left-hand side, okay? And this is the characteristic of such a simple function as ax. If the denominator of this ratio, x subscript 1, decreases so that it approaches x. This is kind of dry. Yeah, okay, so 0 over 0. You see how he's obsessed with 0 over 0? And just rewriting it as dy dx lets things happen. Because 0 over 0, like I said, is an indeterminate form. It could be anything. It just depends. Like I said, it could be 0, it could be infinity, it could be any number. Sometimes it turns out to be a number, like this. It turns out to actually be a number, and it's real. Y equals f of x. The function of x appears on the right-hand side, and it's developed algebraic expression. We call this expression the original function. Modification by differentiation, the primarily derived function, in its final form, obtained by the means of process of differentiation. You have a function, and then you're going to do something to it, derive it, and get a new function out. That's what we're saying. And then this is the basic function, just a cubic function, that he's going to try to do this difference thing to, this difference operator. It's going to be a little bit more tricky, and he's going to get this out. Alright? Now we see an issue here, which is the limit value. And then actually what happens is like these things go to 0, and you're left with the bx. Ax squared, because this goes to 0, this goes to 0. Here's the limit value of the ratios of the finite differences. That is, however small these differences may become, the delta y over delta x. He's being really like picky about it. I don't know. Like I see what he's saying, he doesn't need all this kind of. He's doing a lot of him and han, I feel like. Yeah, so this is what I was saying next, is like when these things go to 0, and this all just goes to x squared. Oh wait, x subscript 1 squared is changed to x squared. Okay, so then there are this doesn't go to 0. These are three things that are equal to each other. Yeah, x subscript 1 plus x is equal to 2x, and we obtain the derived function. There you go. First, in order to obtain derivative, x subscript 1 must be set equal to x. Therefore, strict mathematical sense, x subscript 1 minus x equals 0 with no subterfuge while merely approaching infinitely close. Okay, but that's what we're doing, setting them, close. Nothing symbolic appears in the derivative. So yeah, this is a little dry. He's really just understanding what a derivative is. You know what I mean? Like, I don't know. And then, okay, so we've come across a kind of an interesting problem here. Basically, it's like a to the x power, like 2 to the x power, like 2, then 4, then 8, then 16, then 32, that pattern, having a derivative for that. And it gets a little complicated, and it gets into what you would call series expansion, where it's like a minus 1, a minus 1 squared, a minus 1 cubed, etc. And these are, if you notice, these are flipping, alternating between positive and negative. Positive here, negative here, and negative here. Positive here, and they're all shifted by a minus 1. And then these are getting smaller, 1/2, 1/3, 1/4, 1/5. It would be getting smaller over time. And then this is but this would make a number. Like this would converge to a number. And apparently that's called we're going to look into this, the Napierian logarithm of the number. Natural logarithm, same thing. Okay, so yeah, this would just normalize this into like a, putting that a in front just makes it a whole number. Log a, same thing. So it's the same thing as taking the natural log, but yeah, that's a little more of a sophisticated idea. Oh yeah, and then he did derive this function on his own, which this is a complicated function that we don't really need to go through the derivations of this. It's like, think of the coordinate, or like spherical coordinates, like triangular coordinates, you know what I mean? Like there's a length, this is the tangent function, okay? So you have, a length x, a length a. This is the same thing as like a squared plus b squared equals c squared, okay? We're talking about the exact same thing. There's a squared, there's b squared, there's c squared. We just took the square root of c squared to get c by itself, okay? And then, so that's just a function, and you can derive it, and you'll get this answer, which is a good answer. It's a fun one. Let's see, on the differential, okay, this is the product rule stuff we were talking about earlier, where when you combine two functions, you have to kind of split them apart. It gives you the new derivative. So that's just another, this is more of the, kind of more of the same. That's what I'm saying. It feels like he just understood it. You know what I mean? But there's nothing like groundbreaking here. You know what I mean? Like there's nothing I haven't seen before. See, this is like more of this, see, like, it's repetitive. You know what I mean? This is the second time this has been written. Like, we get it, Karl. Karl, I understand. Does he have anything? Yeah, no. So this is, I was saying earlier, where you keep taking derivatives, that you get 6x plus 2a, then you get 6, and then you get 0. Yup. Karl. Lacking material here, Karl. Is there anything... He keeps on re-deriving the same thing. Okay, this looks like some new stuff. This looks new. There you go. Oh, this is somebody else's analysis. It's in the appendices. Okay, so really he just had the... He really... We get it, Karl. This is also the appendix. So really he was just stuck on defining the derivative, which he did. He's still saying 0 over 0. Have you learned nothing, Karl? And then the rest of it seems to be like critiques, you know, and other notes, things of that nature. Because I saw, yeah, like he's not doing stuff this complicated with pi and polygons, you know, like he avoided the geometry, remember? So I feel like this is about, we've about reached our, I feel like we've about concluded our investigation here. Yeah, these are special functions, like, what is this, a P series? I don't even know. But this isn't anything important that hasn't been, you know, talked about. This as a power series, you know, it converges, like power series converge. So this is convergent, I believe. Yeah, this is convergent. It's just a series expansion, like through the binomial theorem. Okay, that's nice. Let's see, he loves this 0 over 0 equals something. He loves that. It's funny, but it's just funny. Like, you would think with how much he's written about it, he would have gotten over the 0 over 0 like dilemma by now, but he hasn't seemed to. You know, he's 200 pages into this, and we're still talking about how 0 over 0 should make sense when it doesn't. Oh, this is just, I don't know, combining multiple functions, and then, I don't know, this looks like some type of logarithm thing. I'm not sure what's happening here. But I'm about done with this. I don't know how much more. See, now, yeah, like, I could explain what this is, but I'm not. If you know what Taylor expansions are, then sick. But if you don't, then, like, it's a way to approximate functions. Let's just go with that. And you do it by taking continuous derivatives and shifting things. It's kind of what's going on. Let's see if there's anything else. Is there anything? More notes? I like that this note section is blank. It's almost for the reader, you know. Oh, here's a limit. That's the limit. That's what he's been trying to say the entire time, but without saying it like this, without writing it like that. This means the exact same thing that I've described. This is the definition of a derivative. Maybe this isn't the worst intro to calc video for people, but yeah, we're kind of circling the drain here, Karl. I feel like, you know, this is more of the same stuff. Okay, now he's doing a little bit like, no, that's still nothing really much of anything. Alright, well, I think this has been the Karl Marx video, guys. Shout out to Karl Marx. He's I made the joke of calling Jordan Peterson a thought leader in another video, but Karl Marx, he really was a thought leader, you know what I mean? He was stateless for a while. That's tough. And so, yeah, but shout out to Marx. Look at him. He's got a nice vest on. But this has been, you know, a look into his mathematical endeavors. I feel like it was kind of interesting, you know what I mean? Like we said, it was nothing groundbreaking, but it was something, you know. He knew what he was a bright guy, you know what I mean? Like, I see why people listen to him. But as far as math goes, there are just other people who could do it better, you know what I mean? And that's how it goes. He was busy thinking about Marxism all day. He can't be thinking about math. Like, you gotta stick in your lane, that kind of thing. You know, he's trying to be a jack of all trades. I mean, he was clearly a very intelligent person. Go Karl Marx. Shout out Marx. Yeah, this makes me want to be a Marxist even more now. So shout out communism and the communist parties. Yeah, I think, not communism, but socialism rather. Yeah, I'm pro-socialism, and I think that workers should own the means of production. If that's one thing that we've learned in this video, learning about all of his mathematical endeavors. Workers should own the means of production. That's a fact. With that, I hope you enjoyed the video. Leave a like and comment. Let me know what you enjoyed, what you didn't enjoy. Be sure to subscribe if you want to see more stuff like this. Suggest what other videos you want to see from me. More stuff like this, because this was fun, and one of you guys recommended this. So, thank you for the suggestion, and because this is like right up my alley. You know what I mean? Like I said, hope you enjoyed this video. I will talk to you guys soon. Thank you. Love you. Bye.